Hello everyone, and first of all, thanks for the opportunity to talk here at the IEEE International Conference on Software Architecture 2022 on the new and emerging ideas track. I would like to introduce you to our architecture that can be used to deploy ephemeral components on the edge. My name is David Schuster and I'm a research associate at the University of Duisburg-Essen at the chair of software engineering. Within the scope of our research, we focus on hybrid software architectures. So this means we deal with the question of how software must be designed in order to make the best possible use of both the edge in combination with 5G and the cloud. First, I'd like to start the talk with an overview of the content of the presentation. After a brief introduction to cloud and edge computing, I'll present a number of challenges that arise when developing edge-based software architectures. To address a number of these challenges, I'll describe our proposed architecture in more detail below. Afterwards, I'll present the architecture based on a specific use case, and then I will close the talk with an outlook on possible future work. So let's start the talk with a brief introduction to cloud and edge computing. The traditionally approach is that the applications or services are provided by cloud providers in globally distributed data centers. The advantage of this strategy is that these data centers have a huge amount of resources, such as CPU or memory, so that the individual services can be scaled globally and to a very, very large number. The new mobile communication standard 5G uncovers a problem for this cloud deployment strategy. Some mobile applications have network performance requirements, such as a very low latency or an enormous high data rates. Since the data centers are distributed worldwide, such connection properties cannot be guaranteed. To ensure that the 5G properties are used optimally, data processing must therefore take place within the 5G network, and this approach is called edge computing. In general, edge computing is defined as a decentralized data processing in close proximity to the devices. The basic idea is the same as with the cloud. The difference is that the applications and services are provided at the edge of the network. In the context of 5G, this means that the service request can be processed within the 5G network without leaving the network or forwarding the request to the internet. Edge computing is a well-known computing paradigm, so that many research and industry groups have already dealt with. The quasi-standard for edge computing in the context of 5G is called multi-access edge computing and is being developed and continuously expanded by the European Telecommunications Standard Institute. So with the advent of this new computing paradigm, a number of challenges arise in terms of the software architecture. The first challenge is the application design. The question is how we can partition an application in terms of performance, privacy, and data protection requirements. In addition, due to the heterogeneous environment in the edge and the cloud, orchestrating the individual components of an application at runtime is also a key challenge of edge computing. So this means we need a concept to decide when and where the components of an application can be deployed, and perhaps more importantly, how long it should be deployed within the environment. Another important topic in edge computing is context awareness. So to take the best possible advantage of the connectivity features of edge computing, we need to decide which components can be deployed as close as possible to the devices and which components can be deployed in the cloud. In addition, the devices in mobile communication usually move in the environment. Based on this fact, mobility support is also a key challenge for edge computing. So that we have to ask the question, are there any components of the software that need to move along due to movement of the devices? Another important aspect that must be considered in the context of edge computing is security and privacy. So this means that edge-based software architectures must, on the one hand, ensure the secure transmission of data, for example, to reduce the potential for man-in-the-middle attacks, and on the other hand, retain information only as long as it's needed. These aspects include the questions, so which data can be sent to the cloud and which data can remain in the edge, and how long must the data be retained? To address the performance, security, and privacy challenges, we have designed an architecture that allows the deployment of so-called ephemeral components. We define an ephemeral component as an application component, so for example, a set of microservices that is instantiated and deployed on demand but removed after use. In this context, ephemeral components serve a specific purpose. So for example, when multiple users need to temporarily share some data within some application, ephemeral components can serve as the backend to enable this functionality. So it should be mentioned that the data exchange or processing is provided exclusively for the period of explicit use. After this time period, the components are deleted completely without exception. The overall idea of the proposed architecture is to divide the whole system into a management layer, typically residing in the cloud, and several ephemeral components deployed into the edge on demand. The management layer consists of two building blocks which are deployed in the cloud. The ephemeral component administration is responsible for receiving events indicating that users need to work on use cases associated with ephemeral components. In addition, the administration is responsible for user management. So, for example, it provides user access tokens, which the ephemeral components can use for user authentication. The second building block is an implementation of the ETSI multi-access edge computing reference architecture. This system level of the MAC architecture includes a user application lifecycle management proxy and an orchestrator to trigger application instantiation and termination within the edge environment. The ephemeral components are deployed as close as possible to the user equipment. Several instances of the ephemeral components can be running simultaneously but completely autonomous, unaware of each other, and only available to their dedicated users. So next I would like to present our proposed architecture based on a use case. One use case that could benefit from our approach is an application for information sharing between actors in emergencies. After an accident has happened, all relevant data of the emergency are transmitted to the public safety answering point. Initial information such as location, time, information about the environment and type of the emergency will be transmitted to the ephemeral component administration. After saving this incoming data and linking it to a unique ID, the administration initiates the deployment of the new ephemeral component instance by sending the ID and location information of the emergency to the system level of the MAC. The orchestrator of the MAC system uses the position data to calculate the edge host closest to the emergency location. The selected host starts up an ephemeral component on the basis of a predefined image which contains input and output interfaces for important patient data or information about the location of the emergency. After the components have been deployed, the Mac system transmits the ephemeral component's unique URL to the administration, which distributes it to all paramedics and the hospital team to inform them that the patient data is now available. The employees assigned to the emergency can log into the ephemeral component through various clients in order to receive the patient data immediately. Due to a uniform REST API, numerous client systems can be used to display various patient data such as pulse, electrocardiogram, oxygen saturation, temperature, or of course the current location. Also, the hospital information system receives as an additional client system all necessary patient data for further in-house processing in the hospital. After the patient is admitted to the hospital, all data are summarized and sent to the hospital information system. Since all further information is collected in the hospital, the ephemeral component can be shut down from this point on via a termination signal, which is sent from the hospital information system to the administration. The administration forwards the command to the Mac system, which initiates the termination of the ephemeral component on the edge host, which includes the complete and irrevocable deletion of its data. The use case shown demonstrates the advantages of such an ephemeral hybrid application deployment. By shortening the data path, ephemeral components increases security and reduce the probability of such man-in-the-middle attacks. In addition, by limiting the execution time of the components and then terminating the component and completely erasing all data, the approach also increases privacy. By limiting the functionality of ephemeral components on their specific purpose and intentionally omitting other features, the necessary source code is reduced, which in turn reduces code complexity, error potential, and security threats. Last but not least, the reduced functionality of ephemeral components leads to a smaller applications needing less resources and efficiently use edge node capabilities. For future work, we plan to use the architecture as base of the implementation of a currently running research project within a real 5G edge cloud environment. For this purpose, the described use case will be transferred into a real-world scenario. A first experimental deployment in a test environment shows promising results, but an evaluation under realistic conditions is still necessary. Another future work is the integration of mobility support for ephemeral components. In order to ensure that the shortest data path between client and components is consistently available, the architecture must be able to relocate components to other edge nodes depending on the location of the clients. So this results in an optimal use of the mobile network properties and guarantees the uninterrupted use of delay-sensitive client applications. In the current version of the architecture, the client system must be created manually and access to the components must be authenticated by the management system. And for future work, access and authentication to the component based on location would certainly be an interesting extension too. For some use cases, the instantiation of multiple components that communicate and exchange data with each other would be interesting. So this requires a detailed definition of the time duration of the provisioning of each component, which would significantly increase effort for both the management and the orchestration of the components. Well, that brings me to the end of my presentation. Thank you very much for your attention, and if there are any questions, feel free to ask.